Hello everyone and welcome to this showcase of kOS. Today I want to show you this improved launch script I've been making. It's originally from a project of a few years ago and I've been retuning a lot of things. So first of all, what you see right now is just a dumb heavy launch vehicle that is launching something into a lunar transfer orbit. Nothing special right now. It's mostly there to show you that there's something in orbit, which we're going to rendezvous with later. So what I've been proved upon from the previous version is that I've retuned the gravity turn, first of all. The gravity turn is now an inverse exponential function with also scaling factors for different planets depending on orbital velocity but also atmosphere size. I have initially based it off of Kerbin and devised a few calculations and tuned it so that it works with basically any planet. I have yet to test it on a lot of other atmospheric planets, but it works well so far. And the second thing I've altered is the launch heading. Previously, that was just a slider that the user could input, which was a very rudimentary GUI. I've gotten rid of that. Instead, what I have is a boot file that loads a GUI that lets you select a launch script. Then that launch script I have made will let you select a target. If you not, you can select a target yourself through a map or something, or a celestial body. And once selected, you can click launch and it will warp to the correct time and transfer window and then launch for you. Now let's see it in action. You can see here the file you can load through the menu, and once loaded it will let you launch. Once you've selected a target, you can also choose ascending or descending node or just the closest. Now in this case we're going to be targeting that heavy launch vehicle we just sent up because it has a lunar module that we're going to rendezvous with. Now once it's selected, you can click launch like so, and it will warp to the correct time. And it will also calculate your launch heading. In this case, because it's launched from the same launch platform at a 90-degree heading, this one will be basically 90 degrees. And you can also see that in the terminal, the calculation for the azimuth that it needs to launch towards. Now it does have a little bit of timing that I have set, so it doesn't actually warp to the exact launch time. It actually leads a little bit so that it can catch up due to rotational correction. Since the Earth is spinning, obviously you have to be earlier or later to end up with a correctly aligned orbit. Now you can see we're finally off the ground, and in a moment it will start to do the gravity turn. So when calculated, it will initially launch towards the azimuth that it's calculated, but eventually, due to drifting, when you're not exactly on the equator, your prograde vector will actually drift away from the heading you initially started at due to your inclination changing. You're always heading towards the equator and overshooting it, which means that it's actually inefficient to keep launching towards that heading. So instead, it calculates these vectors that you can see visualized on the screen to first take the initial vector, the up vector that pointed up from the ship's launch site, and then a constantly updating green up vector that is up from the ground relative to where the ship is right now. And if you take the cross product of those two vectors, you can see it gives the yellow rotation axis vector. That rotation axis vector is then used with the green vector for another cross product to get the target vector. And once you get the target vector, you can add the pitch that you want for the gravity turn, or in this case, another function that will try to maintain the apoapsis at a certain distance from the craft, which I've also tuned so that it can work with a lot of differently powered upper stages. Now, as previously described, this function will initially limit the pitch to at least 5 degrees above horizon, and if the apoapsis gets too close or even behind us, it will pitch up more and more, like you can see right now. But when the orbital velocity, or sorry, the ship's velocity is greater than a certain factor of the orbit velocity, then it will also allow it to pitch down so that it can try to keep the apoapsis at a certain distance and not let it go all the way to the opposite side. Now, this is eventually inevitable unless you pitch down by a lot, but that would be inefficient. So instead, it will try to get as far as possible, and then once the apoapsis is above a certain point, or the apoapsis is too far ahead of the ship, it will cut the engines, it will then warp to close to the apoapsis, and then circularize until the periapsis is within a certain margin of the apoapsis. Now, this is not implemented right now, but I intend to eventually tune that very gravity turn that I've spent a lot of time refining, which is now just down to two very easily changeable factors, which can then determine a desired orbit altitude, which right now it does not have. It will just keep burning prograde until the apoapsis is at least a certain margin above that body's atmosphere. I think it's 1.5 times the atmospheric height, and then once it gets there, it will circularize, which means that you don't have a lot of flexibility in your final orbit, but that's something I intend to keep working on. Now I'm going to let the launch play out one more time and add some visual demonstrations to hopefully better illustrate what I'm talking about. Here you can see the first sketch I used while making this script, and then a more refined drawing. You get initially the up vector that points from the launch site up towards space, and once the ship has turned over enough, which is usually just a few 100 meters, then the new up vector, even though it's a very small angular difference, is already quite aligned with where the circle path needs to be. Now, the reason that this works is, as you can see, the rotational axis vector, you can also project it from the center of the Earth. And what you'll find is that this rotational axis vector is perpendicular to the great circle that is outlined on this illustration. In fact, at every point on that great circle, the up vector is entirely orthogonal to the rotational axis vector. This means that when you draw all those up vectors from the respective points on the great circle, you will actually find all the vectors in space that are on the orbital plane. And what the effect is that when you take the cross product out of any two local up vectors, or in our case, the original up vector and the current up vector, that you will find a vector whose eigenspace is aligned with the rotational axis for our path. Which is a beautiful thing, because that allows us in turn to take the cross product of that axis vector that does not actually change as long as the path is followed correctly, to then find another vector that is our parallel vector, i.e. the vector that follows that great circle, as shown here. Now, if you look at the terminal right now, you can see the rocket is not pitched over enough, and you can see the rotational axis vector is still being calibrated, so to speak, which is why I added a 30-degree safety margin in. So that means the rocket will first pitch over by 30 degrees, and once it's pitched over by 30 degrees or more, it will follow that great circle path with the vectors I described. Moving on, there are some other upgrades I would like to tell you about. First of all, now the rocket actually stages itself. I've tried to do this with a previous script, but then I used part tagging, which means that you give the part a specific tag or name in the craft file editor so that kOS can recognize the part. This obviously is not ideal, as when you rename it with just one character wrong, or not the correct amount of spaces or special characters, it will not recognize it, and that means that the staging will not happen properly. It also is very difficult to make it very adaptable to different types of launch profiles, say side boosters, dual stage, triple stage, or a combination of those. And while I do have to say it's still a work in progress and it's not finished yet, it has successfully staged every rocket thus far, provided you make every staging event 2 stages in the editor. The reason that that's currently necessary is because the staging function that is called from another script I've written is a dual stage, which means that first it will stage and then it will wait because it lets you use RCS or whatever other methods to settle fuel in the tanks because it's built for a real solar system and realism overhaul. And then it will stage again after the fuel settled after a few seconds. Which does mean that side boosters will need an extra stage. The first one to actually separate the boosters, and the second one just as a dummy stage so that the staging function does not accidentally stage the next stage while you're still running. The way that the staging actually works is that it first starts at 0, as in it assumes 0 thrust, and then it will increase the thrust every time it sees a higher output thrust. And once the thrust has stabilized, it will wait until it sees the thrust drops below 90 or 95% from that initial thrust. And now you can see the staging. It's run out of thrust, it stages, it waits, uses RCS to settle the fuel, and then after a few seconds it ignites the second stage. How about that? Thank you for watching, and I hope my explanation finally made a little sense. I really like the fact that I can use visual illustrations like the drawings I showed you earlier and just physically showing the process, because otherwise I have no idea how I would even put this into words. It is all very graphical, I would say, and without the graphics of the graphical element, it's kind of hard to convey the meaning. So, sorry for my rambling, and I hope that it makes a little sense now. Bye!